Hello! Welcome to Squid Essays. Inking your academic pen. My name is Julie and I will be your instructor as we read through digital signal processing. The article source is embedded in the video description below. Feel free to read along. Please note that you can get a custom, plagiarism-free essay for as little as $10 a page at Squid Essays. The link is in the description. Digital signal processing, DSP, is concerned with the representation of the signals via sequence of numbers or symbols and the processing of these signals. Digital signal processing and analog signal processing are subfields of signal processing. DSP includes subfields like audio and speech signal processing, sonar and radar signal processing, sensor array processing, spectral estimation, statistical signal processing, digital image processing, signal processing for communications, biomedical signal processing, seismic data processing, etc. Since the goal of DSP is usually to measure or filter continuous real-world analog signals, the first step is usually to convert the signal from an analog to a digital form by using an analog-to-digital converter. Often, the required output signal is another analog output signal, which requires a digital-to-analog converter. Even if this process is more complex than analog processing and has a discrete value range, the stability of digital signal processing thanks to error detection and correction and being less vulnerable to noise makes it advantageous over analog signal processing for many, though not all, applications. Today there are additional technologies used for digital signal processing including more powerful general-purpose microprocessors, field programmable gate arrays, FPGAs, digital signal controllers, mostly for industrial apps such as motor control, and stream processors, among others. DSP domains. In DSP, engineers usually study digital signals in one of the following domains: time domain, one-dimensional signals; spatial domain, multidimensional signals. They choose the domain in which to process a signal by making an informed guess, or by trying different possibilities, as to which domain best represents the essential characteristics of the signal. A sequence of samples from a measuring device produces a time or spatial domain representation, whereas a discrete Fourier transform produces the frequency domain information, that is frequency spectrum. Autocorrelation is defined as a cross-correlation of the signal with itself over varying intervals of time or space. Signal sampling. With the increasing use of computers, usage of a need for digital signal processing has increased. In order to use an analog signal on a computer, it must be digitized with an analog-to-digital converter, ADC. In the discretization stage, the space of signals is partitioned into equivalence class and quantization is carried out by replacing the signal with representative signal of the corresponding equivalence class. In the quantization stage, the representative signal values are approximated by values from a finite set. Sampling theorem states that a signal can be exactly reconstructed from its samples if the sampling frequency is greater than twice the highest frequency of the signal. In practice, the sampling frequency is often significantly more than twice the required bandwidth. A digital-to-analog converter, DAC, is used to convert the digital signal back to analog. The use of a digital computer is a key ingredient in digital control systems. Time and space domains. The most common processing approach in the time or space domain is enhancement of the input signal through a method called filtering. Filtering generally consists of some transformation of a number of surrounding samples around the current sample of the input or output signal. There are various ways to characterize filters. For example, Section 8 linear filter is a linear transformation of input samples. Other filters are nonlinear. Linear filters satisfy the superposition condition, that is, if an input is a weighted linear combination of different signals, the output is an equally weighted linear combination of the corresponding output signals. Section 8 causal filter uses only previous samples of the input or output signals, while a non-causal filter uses future input samples. A non-causal filter can usually be changed into a causal filter by adding a delay to it. Section 8 time invariant filter has constant properties over time. Other filters such as adaptive filter change in time. Section some filters are stable, others are unstable. A stable filter produces an output that converges to a constant value with time, or remains bounded within a finite interval. An unstable filter can produce an output that grows without bounds, with bounded or even zero input. Section A. Finite impulse response, FIR, filter uses only the input signal, while an infinite impulse response filter, IIR, uses both the input signal and previous samples of the output signal. FIR filters are always stable, while IIR filters may be unstable. Most filters can be described in Z domain, a superset of the frequency domain, by Thira transfer functions. A filter may also be described as a difference equation, a collection of zeros and polisor, if it is an FIR filter, an impulse response or step response. The output of an FIR filter to any given input may be calculated by involving the input signal with the impulse response. Frequency domain, signals are converted from time or space domain to the frequency domain usually through the Fourier transform. The Fourier transform converts the signal information to a magnitude and phase component of each frequency. Often the Fourier transform is converted to the power spectrum, which is the magnitude of each frequency component squared. The most common purpose for analysis of signals in the frequency domain is analysis of signal properties. The engineer can study the spectrum to determine which frequencies are present in the input signal and which are missing. Filtering, particularly in non-real-time work, can also be achieved by converting to the frequency domain, applying the filter and then converting back to the time domain. This is a fast, n log n, operation, and can give essentially any filter shape including excellent approximations to brick wall filters. There are some commonly used frequency domain transformations. For example, the stream converts a signal to the frequency domain through Fourier transform, takes the logarithm, then applies another Fourier transform. This emphasizes the frequency components with smaller magnitude while retaining the order of magnitudes of frequency components. Frequency domain analysis is also called spectrum or spectral analysis. Applications. The main applications of DSP are audio signal processing, audio compression, digital image processing of the video compression, speech processing, speech recognition, communications, radar, sonar, seismology, and biomedicine. Specific examples are speech compression and transmission in digital mobile phones, room matching equalization of sound in HiFi and sound reinforcement applications, weather forecasting, economic forecasting, seismic data processing, analysis and control of industrial processes, computer-generated animations movies, in process of medical imaging like CAT scans and MRI, MP3 compression, image manipulation, high-fidelity loudspeaker crossovers and equalization, and audio effects for use with electric guitar amplifiers. Implementation. Digital signal processing is often implemented using specialized microprocessors. These often process data using fixed-point arithmetic, although some versions are available which use a floating-point arithmetic and are more powerful. For faster applications, FPGAs might be used. Beginning in 2007, multi-course implementations of DSPs have started to emerge from companies including Freescale and Stream Processors, Incorporated. For faster applications with fast usage, ASICs might be designed specifically. For slow applications, a traditional slower processor such as a microcontroller may be adequate. Techniques. Section bilinear transform, section discrete Fourier transform, section discrete time Fourier transform, section filter design, section LTI system theory, section minimum phase, section transfer function, section Z transform, section Gortzel algorithm, section S-plane, related fields, section analog signal processing, section automatic control, section computer engineering, section computer science, section data compression, section electrical engineering, section information theory, section telecommunication, bilinear transformation. The bilinear transform is used in digital signal processing and discrete time control theory to transform continuous time system representations to discrete time and vice versa. The bilinear transform is a conformal mapping, often used to convert a transfer function HA(S) of a linear, time invariant, LTI, filter in the continuous time domain, often called an analog filter, to a transfer function HD, Z, backslash of a linear, shift invariant filter in the discrete time domain, often called a digital filter. Although there are analog filters constructed with arch-coupled devices that are filters, it positions function that is an exact mapping of the Z-plane to the S-plane. When the Laplace transform is performed on a discrete time signal, with each element of the discrete time sequence attached to a correspondingly delayed unit impulse, the result is precisely the Z-transform of the discrete time sequence with the substitution of begin align Z and equals EST and equals frac EST /2 EST /2 and approximately frac 1 plus ST/2 1 ST/2 and align, where T is the sample time, the reciprocal of the sampling frequency of the discrete time filter. The above bilinear approximation can be solved for S or a similar approximation for S equals 1 per ton ln Z can be performed. The inverse of this mapping is begin align S and equals frac 1 T ln Z and equals frac 2 T left frac Z1 Z plus 1 plus frac 1 3 left frac Z1 Z plus 1 right 3 plus frac 1 5 left frac Z1 Z plus 1 right 5 plus frac 1 7 left frac Z1 Z plus 1 right 7 plus dots right and approximately frac 2 T frac Z 1 Z plus 1 and approximately frac 2 T frac 1 Z minus 1 1 plus C minus 1 and align. The bilinear transform essentially uses this first order approximation and substitutes into the continuous time transfer function S left arrow frac 2 T frac Z 1 Z plus 1. The bilinear transform is a special case of a conformal mapping, defined as stability and minimum phase property preserved. A continuous time causal filter is stable if poles of its transfer function fall in the left half of the complex plane. A discrete time causal filter is stable if the poles of its transfer function fall inside the unit circle in the complex Z-plane. Likewise, a continuous time filter is minimum phase if the zeros of its transfer function fall in the left half of the complex S-plane. A discrete time filter is minimum phase if the zeros of its transfer function fall inside the unit circle in the complex Z-plane. Then the same mapping property assures that continuous time filters that are minimum phase are converted to discrete time filters that preserve that property of being minimum phase. As an example, take a simple low-pass RC filter. This continuous time filter has a transfer function begin align HA/S and equals frac 1 SCR plus 1 SC and equals frac 1 1 plus RCS and align. If we wish to implement this filter as a digital filter, we can apply the bilinear transform by substituting forced formula above. After some reworking, equals HA left frac 2 T dot frac left EJ omega T /2 EJ omega T /2 right left EJ omega T /2 plus EJ omega T /2 right right HD Z equals HA left frac 2 T frac Z1 Z plus 1 right HD EJ omega T equals HA left frac 2 T frac EJ omega T1 EJ omega T plus 1 right filter design. Filter designates the process of designing a filter, which is a shift invariant filter, which satisfies a set of requirements, some of which are contradictory. A filter can be designed by process optimization problem where each requirement contributes with a term to an error function which should be minimized. Certain parts of the design process can be automated, but normally an experienced electrical engineer is needed to get a good result. Typical design requirement. Typical requirements which are considered in the design process are: section, the filter should have a specific frequency response. Section: the filter should have a specific impulse response. Section: the filter should be causal. Section: the filter should be stable. Section: the filter should be localized. Section: the computational complexity of the filter should be low. Section: the filter should be implemented in a particular hardware or software. The frequency function. Typical examples of frequency function are: section: a low-pass filter is used to cut unwanted high-frequency signals. Section: a high-pass filter passes high frequencies fairly well. It is helpful as a filter to cut any unwanted low-frequency components. Section: a band-pass filter passes a limited range of frequencies. Section: a band-stop filter passes frequencies above and below a certain range. A very narrow band-stop filter is known as a notch filter. An all-pass filter passes through all frequencies unchanged, but changes the phase of the signal. This is a filter commonly used in phasor effects. An important parameter is the required frequency response. In particular, the steepness and complexity of the response curve is a deciding factor for the filter order and feasibility. A first-order recursive filter will only have a single frequency-dependent component. This means that the slope of the frequency response is limited to 60 per octave. For many purposes, this is not sufficient. To achieve steeper slopes, higher-order filters are required. Techniques details. The development of DSP microprocessors has made DSP the method of choice in recent years. Unfortunately, real-time DSP requires relatively expensive DSP microprocessors. If the operations needed to transfer the data to and from the processor are included, it turns out that the processor must perform faster than 400 mFLOPS if programmed in assembler language and faster than 600 mFLOPS if programmed in a high-level language such as C. Details. In this, each frame of the imaging video signal, in which the pixels appear in row order, is filtered by an analog filter, transposed to column order, filtered again by an analog filter, and transposed back to row order to give the output video signal. Typically, the two analog filters are identical. It has very low noise-to-signal ratio. The preferred embodiments in detail. The present invention is of a method and device for processing analog signals, such as video signals, that represent data acquired in a two-dimensional field. Specifically, the present invention can be used to filter video signals in real time. The principles and operation of analog according to the present invention may be better understood with reference to the drawings and the accompanying description. Pipeline bus structure is used for processing successive frames of video signals according to this method. The double solid lines represent the flow transfers the resulting digital signals to communications lines 14. DA converter 26 receive digital signals from communications lines 10 and transform them to analog signals. The operation of the device is best understood from a narrative of signal flow through the device during the processing of several successive frames of video signals. First video frame, stored in memory bank 36 in digital form and in row order, is read from memory bank 36 and sent to DA converter 26, where the first video frame is converted to an output analog signal. All this is done after the receipt of the third input video frame by filter 40 and before the receipt of a fourth input video frame by filter 40. The processing imposes a uniform delay of 2 frame durations on the signal. Modern analog video amplifiers impose delays of on the order of 2 nanoseconds on the incoming signals. This is about 4% of the duration of one standard analog video pixel, and therefore is negligible. The read-write cycles of modern memories are on the order of 8 nanoseconds, also considerably shorter than the duration of one standard analog video pixel. In an alternative embodiment of the present invention, the fact is exploited that once a memory location has been read from during a given frame duration, the data that was stored in that memory location is no longer needed and may be written over. It has only 2 memory banks in this embodiment. In this embodiment, during the duration of any one video frame, as twice filtered row order data are read from one of the memory units. The results of video processing, using the prototype system mentioned above. His method has many potential applications in microscopy, military target acquisition, surface defect detection, and medical surgery. In the latter application, the present invention can enable a physician at a remote location to see the textures and tiny details of a surgical patient's body tissues. Conclusion. This term paper describes the various techniques for analyzing the analog signals. I have made my full effort to cover every technique and explain them in detail. Digital signal processing also covered in this paper along with a new invention which is recently used for signal processing. References: 1. Google search engine. 2. Wikipedia. 3. E-book on techniques of DSP transformations. 4. Analog Communications by J.S. Cater. 5. Professor J.S. Dillon, Communications. Please be aware that the free essay that you were just reading was not written by us. This essay, and all of the others available to view on the website, were provided to us by students in exchange for services that we offer. This relationship helps our students to get an even better deal while also contributing to the biggest free essay resource in the UK. Thank you for taking your time to listen to me. I hope you enjoyed learning about digital signal processing as much as I did. Kindly remember that you can get a custom, plagiarism-free essay at Squid Essays for as little as $10. The link is in the description. See you next time.